Good afternoon, everyone. My name is Han. It's my pleasure to present here. My topic is a novel continuous subject boundary detection algorithm with a two-phase area refinement mechanism for wireless mobile sensor networks. And this is my outline. My outline includes introduction, related works, proposed methods, simulations, and the conclusions. There are lots of applications in wireless sensor networks. One of the most important scenarios is that detecting and tracking the continuous object. A continuous object usually refers to the gas event, because gas leakage may cause the explosion and damage to life property. So the WSN can be utilized to avoid the explosion by detecting, tracking, and visualizing the area of the continuous object. There are several studies focused on this issue. Some of them use the cluster structure. The DT-CLDD and the CLDA construct the cluster to reduce the communication overhead, because each cluster has one cluster head, and only cluster head can transmit data to a single node. Therefore, lots of communication overhead can be reduced. Then the others use the penalization algorithm. The DGAS use the penalization algorithm such as Gabriel graph and the related neighborhood graph to determine the boundary area of a gas event. Moreover, they found the optimal number of sensor nodes to deploy in the field. So the above observation gives us the idea to detect the continuous subject with the mobile sensor nodes. In this paper, a continuous subject detection algorithm with a two-phase area refinement mechanism is proposed. And in this part, we divide the methods into three stages. First is the boundary detection mechanism. Second is the moving algorithm, and the third is the boundary refinement mechanism. After all sensor nodes are deployed in the field, the first task is to figure out the sensor, which are the inner nodes or the outer nodes. A sensor is called an inner node when its sensing value of the gas event is higher than the predefined threshold. Then this node will become an inner node. And likewise, a sensor is called an outer node when its sensing value is lower than the predefined threshold. Then, the sensors in the set of iron use the grand hand scan algorithm, which is a convex hull method, to find the inner boundary nodes and the inner boundary area. After that, we can find the outer boundary nodes by computing the Euclidean distance between the IBM and its one-half neighbors. So now we can obtain the outer boundary area and the inner boundary area to estimate the initial dangerous area. Then we propose the moving algorithm. At first, the moving direction should be determined by calculating the direction vector according to the neighbors of each node. And there are two situations when we calculate the direction vector. The first is that the sensor node only has one neighbors. In this case, we only need to calculate their coordinate each other. Then we will get a vector with the direction. And the other is that the sensor node which has lots of neighbors. In this case, each neighbor's positions are summed to get the resultant vectors as the equation. Then we can use the resultant vector to calculate the vector with the direction. Then, to refine the inner boundary area and the outer boundary area, the moving node should not cross the boundary at the same time. So, the moving distance of each mobile sensor is controlled according to the proportion of the distance between the mobile sensor and its one-half neighbors. Besides, a lock node mechanism is also proposed in this paper to prevent the sensor node from crossing the boundary line again and again. Then the moving method will not stop until all distance between the IBM and the neighbors are smaller than the half of the communication range. Then the boundary refinement mechanism is proposed. Some OBN which move inwards will not become the OBN in the next round anymore. Therefore, the BIM authorized these nodes to refine the boundary area of the continuous object. At first, The BRN determines which candidate OBN can be replaced by the node, and the candidate OBN in the following case cannot be updated and deleted. Case 1. The candidate OBN finds no neighbors in its communication range. Case 2. The candidate OBN has only one neighbor and this neighbor is also an OBN. Case 3. The candidate OBN has lots of neighbors and the distance from each and the distance is farther than the distance from itself to its one-half neighbors. Then simulation. Our environment assumption is that the continuous object presents us an irregular shape and unity fields, and the sensor nodes are randomly deployed in the 800 multiple 800 field. The number of sensor nodes is from 100 to 900 and the increments to 100. The communication range of each sensor node is 60 to 80, and the increment is 5 meters. The proportion of the moving distance from half of distance to 1/4 of distance. Then the evolution matrix includes the inner boundary area, the outer boundary area, the false positive area, the true negative area, and the refined OBA. The FPA means that the area is in the OBA but not in the area of the continuous object, which means it is the superfluous area for the OBA. Then the TNA means the area is in the continuous object but not included in the OBA, which means the OBA ignores the dangerous area. And we also analyze the result of the impact of different variants. And in this case, we can show the precision of the IBA and the OBA. And the precision of the IBA and the OBA should be close to 1, which is the best. Then we can see when the number of sensor nodes is less than 300, the precision of IBA and OBA is not accurate because the density of sensor nodes is not enough to construct a good convex pool. Then, when the number of sensor nodes increase, 2 of them, the precision of them also increases too. Then, the OBA has the smallest area when the communication range is set to 60. Then the result of the FPA and the TNA should observe the curve by going with the result of the OBA. Then, in pace with the increment of the number of sensor nodes, the FPA increase because it should be same as the tendency of the OBA. Then, when the number of sensor nodes is 900, all of the FPA is higher than 20,000, which means the OBA encircles almost whole the continuous object. Then we can verify this true by evaluating the DNA. So in the same amount of nodes, the DNA approaches 0. So this true can be proved. Then figure 5 shows the comparison between the result of the initial and the result of the refined OBA. Then we can see the result of the 700 and 900. Their results are similar. Their division is at less than 3%. So when the number of sensor nodes, then the communication range is 780. The first refining mechanism improves 35% accuracy on detecting the continuous object, and the second refinement mechanism contributes an additional 3%. So the refined OBN is better than the initial OBA, 38% in total. And then we will analyze the impact of the number of sensor nodes and the proportion of the moving distance. The influence of the numbers of sensor nodes is the same as the conclusion in the previous subsection. So we only analyze the proportion of the moving distance. Then when the number of sensor nodes is 900, the performance of IBA in 1/3 and 1/4 of distance are almost the same. And the OBA also. Then we can see the FPA and the TNA. When the number of sensor nodes is 900, the performance of 1/3 and 1/4 are still almost the same. However, the performance of the half of distance is not as good as the other two, but it can converge fast. And the figure 10 shows the comparison between the results. We can see all of the ROBA is smaller than the initial OBA. However, the other moving distance do not affect the result of the refinement mechanism. So in this paper, a novel continuous object boundary detection algorithm with a two-phase area refinement mechanism is proposed for wireless mobile sensor networks. And the experiment result shows that the moving procedure improves 35% than the initial OBA. Then the second phase boundary refinement mechanism improves 3% additional. Therefore, the proposed method improved 38% precision compared with the initial OBA in total. Thanks for your attention.